All right. There's a quiz at the end of class. So we'll do that in like the last 10 or 15 minutes of class. I'm going to start with number 2 from the assignment. I think a lot of people had questions about that. So I gave you the matrix relationships between stress and strain. And then it just asks a lot of questions about what's the dependency of, like, what it's really asking is what stress values do you need in order to calculate a certain strain value? Um, like, what if you're not given all of the stresses? Are there any strain values that you could still calculate? You know, so let's think about that. Okay, so we have this relationship that says the Voigt strain is equal to the compliance matrix times the Voigt stress. And we have all the elements of these things. And so I'm going to write this out as, so this is what we were talking about here, but I'm going to write it out again. So we have EXX, just writing out the elements of this, EYY, EZZ, lambda YZ, lambda XZ, lambda XY. And if I multiply out the right side of this equation, because you have all those zeros in the compliance matrix, what you get is, for the first element, you get 1 over E times sigma XX minus nu over E times sigma YY minus nu over E times sigma ZZ. Okay, so what that says is EXX is equal to this expression. Okay, so you don't need any of the shear stresses in order to calculate EXX. Okay, all you need is the 3 normal stresses. Okay, so let's go down to the next one. And if you multiply out the next line of the matrix equation, you get negative nu over E times sigma XX plus 1 over E times sigma YY minus nu over E times sigma ZZ. And so the dependence is the same, but the equation is a little bit different. Then the next one, EZZ is equal to nu over E sigma XX minus nu over E times sigma YY plus 1 over E times sigma ZZ. And now we're going to the equations for the stress, the shear strain elements. Because of all the zeros, this just comes out to be 2 times 1 plus nu over E times tau YZ. The next one is 2 times 1 plus nu over E times tau XZ. And the last one is 2 times 1 plus nu over E times tau XY. And so for the questions that are just asking about the dependency, you can see that EXX depends on all 3 normal stresses. EYY depends on all 3 normal stresses. EZZ depends on all 3 normal stresses. But gamma YZ only depends on the YZ shear stress. The XZ shear strain only depends on the XZ shear stress. And the XY shear strain only depends on the XY shear stress. And then the ones that ask for the equations, so this says, okay, what's the equation? What's the algebraic relationship for EXX? It's 1 over E sigma XX minus nu over E sigma YY minus nu over E sigma ZZ. And you can just go down like that. Okay. So there are cases where even if you don't know all of the stresses, you can still calculate certain strains. Which ones you can calculate depend on these dependencies. All right. Normally, when people teach this class, like if you look at most textbooks for this class, it's taught as one by one equations like this. They don't go into like matrix relationships or anything, but it just means that you have to learn a million equations when really the equations have kind of a simple matrix form, you know. But any questions about that?
And that's just multiplied when we get the voids
Exactly. So this second vector is what you get from multiplying the compliance matrix on the left with the Voigt stress on the right. Because it's like, let me do one line of that, you know. So
and it's a 6x6 matrix, right?
yeah, and so remember the compliance matrix first line looks like this. Then you have all this down here. And you're multiplying that by the Voigt stress that looks like this. And so that's a dot product of this with this, and what you get is this equation over here. Okay. Any other questions about this problem? Any other homework problems you want me to talk about? All right. So last time we started talking about the tensile test, the way that you get these values. And so now I'm going to go through kind of like how you would do the tensile test, how you would use it. So let's say that, so we're doing a tensile test of a material. And let's say that our sample piece looks like this. We have a length this way of 0.1 meters, which is 10 centimeters. We have a width this way of 0.02. So 2 centimeters. And then 0.02, that looks right. And then this one that definitely is not drawn to scale. Let's say that this thickness is 0.01, so 1 centimeter. Okay, so that's the sample piece that we're going to put in the mechanical testing machine. And we're going to use a coordinate system like this. The x-axis always is along the line of loading. The y-axis, I'm going to say, is this way although that's arbitrary. And then the z-axis is this way. And we're going to apply forces to this thing. We're going to put it in the jaws, and we're going to stretch it like this. And that tensile force is 5,000 newtons that we're going to apply to it. Okay, so notice that if you're just talking about a single force like this, you're not going to get that whole readout of the tensile test that I gave you last time. You're just going to get 1 point on that graph of the stress versus strain curve. Can you picture what I mean? But let's say that when you apply these forces, what you measure is a new length, a deformed length of 0.10003. So you can sort of get a sense of what kind of precision you need in these measurements to measure this stuff accurately. And then the width that started out as 1 centimeter becomes 0.009949 and then a 2. And we want to first figure out the Young's modulus and the Poisson's ratio. Then we want to calculate the compliance matrix. And then we'll keep using this example after that. But let's just do this for now. Like, let's say this is 2 teams of people. So the first day, the experimental people are going to go do this mechanical testing. They're going to come up with those parameters, come up with the compliance matrix, and then the modeling engineers are going to use it the next day. We'll talk about that. Okay. So first, in order to calculate Young's modulus, we need to calculate the stress in the x direction. And that is going to be the tensile force divided by the cross-sectional area that's like resisting deformation. So think about what dimensions matter to the cross-sectional area here. What are we going to multiply together for the area?
The flat face or like the
So what you have to do is think about, like, what is the area that if you increase it is going to make this deform less, and if you decrease it, it's going to make it deform more. And that area is this one. It's always an area perpendicular to the loading. And so this is going to be the 1 centimeter times the 2 centimeters. Okay, the height doesn't matter in the least as far as the strength goes. And so if you calculate this, that's 5,000 divided by 0.0002, and that comes out to be 2.5 times 10 to the 7 pascals. A pascal is a Newton per meter squared. So this is newtons, this is meters squared. And then the other thing we need to calculate E, Young's modulus, is the strain in the loaded direction. So that is going to be the deformed length, so 0.10003 minus the undeformed length of 0.1 divided by the undeformed length. This is meters divided by meters, so you end up with something unitless. And this gives you 0.0003 divided by 0.1, which is I'm missing a zero. And so this comes out to be 3.0 times 10 to the minus 4. Okay. In that rough ballpark range of like the biggest strains that we are going to trust in this class. And so now we can calculate E. So the stiffness is equal to 2.5 times 10 to the 7 pascals divided by 3.0 times 10 to the minus 4. And we end up with 83.3 repeating times 10 to the 9 pascals. Or in other words, 83.3 gigapascals. Any questions about that? And now we're going to do, yep.
Do you choose to use the X because that's the way it's being stretched?
Yeah, exactly. So for E, everything you're using is in the direction of the loading.
Okay.
Yep. And since we always put the X axis in that direction for the tensile test, it's always the X values you're using.
Okay.
Now for Poisson's ratio. We need one more thing. We already have the EXX strain. We need either the EYY or the EZZ strain. Either one will work fine. So what we have is the Y, well, the ability to calculate the Y. So this is going to be equal to the deformed length, which is 0.00 and then 4 nines and a 2, minus the undeformed length in that direction, divided by the undeformed length. And we get negative 8.0 times 10 to the minus 5, and it's unitless. Now the Poisson's ratio is negative EYY, that could be EZZ2, divided by EXX. And so we have negative 8.0 times 10 to the minus 5 divided by 3.0 times 10 to the minus 4. And we get a Poisson's ratio of 0.26 repeating. Is that within the possible range of Poisson's ratios?
Yeah,
0 to 0.5, yep. And we do expect most things to hover somewhere close to 0.3.
That's metals, right?
Yeah, but actually concrete is pretty close to 0.3 too, I think. But anyways, yeah, this is close to 0.3. Everything about this looks very reasonable. What about the Young's modulus? So 83.3 gigapascals, is that in a reasonable range?
Yes, it's measured in
Gigapascals, yep. And so metals are usually about 100 to 250 gigapascals. Other engineering materials might go down to 50 gigapascals or something, but this is right in that range. Okay, well, so now we have these two values, E and Poisson's ratio. And now we can fill out the compliance matrix. So the compliance matrix is the thing that says, I'm not going to write this all out, but 1 over E, negative nu over E, negative nu over E, 0, 0, 0, goes all the way down at 6 by 6. And so, well, let's just, there are only 3 element values in this whole matrix. The first one is 1 over E. And 1 over E is, if you divide that out with the, so 1 divided by 83.3 times 10 to the 9. I'm going to do this all in SI units. You get 1.2 times 10 to the negative 11, and this is 1 over pascals. The second element value that we get is negative nu over E. So that is negative 0.26 repeating divided by 83.3 times 10 to the 9. And that one gives you negative 3.2 times 10 to the minus 12, 1 over pascals. And then the only other element value is 2 times 1 plus nu divided by E. And so that is 2 times 1 plus 0.26 repeating divided by 83.3. The 83.3s are all repeating, by the way, times 10 to the 9. And that one gives you positive 3.05 times 10 to the minus 11, 1 over pascals. And so now let's fill in this compliance matrix using these values. So we have 1.2 times 10 to the minus 11, negative 3.2 times 10 to the minus 12, negative 3.2 times 10 to the minus 12, 0, 0, 0. Then the second row, negative 3.2 times 10 to the minus 12, 1.2 times 10 to the minus 11, negative 3.2 times 10 to the minus 12, 0, 0, 0. Then the third row, negative 3.2 times 10 to the minus 12, negative 3.2 times 10 to the minus 12, 1.2 times 10 to the minus 11, 0, 0, 0. Now the fourth row, we have 0, 0, 0. And in the fourth spot, we have 3.05 times 10 to the minus 11, and then 0, 0. In the fifth row, that value just moves over 1. So 0, 0, 0, 0, 3.05 times 10 to the minus 11, 0. And then the last one, all zeros except that value in the last spot. And all of this is in units of 1 over pascals. Okay, so now we have this thing. We have this material. Maybe we grew this thing as a crystal or whatever. Like we mixed this alloy, and we have this matrix that defines the relationship between deformations and loads. Okay, and now we're going to say the next day. The modeling team determines that during some application, a point in the material will have the stress of, I just made these up, but let's say there's going to be a stress tensor of 2 times 10 to the 7, negative 1 times 10 to the 7, 0, negative 1 times 10 to the 7, 0, 0, 0, 0, 8 times 10 to the 6. And this is in pascals. And we want to know what the deformation is. So what will the Voigt strain be at that point? Okay. Well, the way we're going to calculate this is we're going to say EXX, EYY, EZZ, gamma YZ, gamma XZ, gamma XY is going to be equal to that compliance matrix. And I'm not going to fill in the values. I'll just call this the compliance matrix. But remember that this is the compliance matrix that we figured out up here. Okay, because that's the compliance matrix that represents this material times the stress in its Voigt form. So that's going to be 2 times 10 to the 7, 0, 8 times 10 to the 6, and then 0, YZ is 0, XZ is 0, and XY is negative 1 times 10 to the 7. And you have to remember to make these units match. So when you're using the compliance or the stiffness matrix, I would just recommend always putting it in SI units. Okay, like if you leave the compliance matrix in gigapascals and you put your stress in pascals, nothing is going to be right. Okay. But now if you multiply, do this matrix multiplication, you get 0.000214. I don't know why I did this in standard notation, but then the YY element of the Voigt strain is negative 0.00090. The z direction normal strain is 0.4032. And then you have 0, and then 0, and then negative 0.30304. And so what this says, if like you could sketch the parallelepiped that comes out of this calculation, you get a little bit of stretch in the x direction, a little bit of compression in the y direction, a little bit of stretch in the z direction, and then the angles between the x and y, positive x and positive y faces becomes a little more obtuse. Okay, becomes greater than 90 degrees. Any questions about that? So you do this one tensile test for the material, and then you use that compliance matrix that you got out with any of the stresses that you calculate. Okay. You also could go the other way. So for part D, let's say now the modeling team determines that the Voigt strain at a point is, so let's say 1.5 times 10 to the minus 5, 0, negative 2.5 times 10 to the minus 5, negative 6.0 times 10 to the minus 5, 0, 0. And we want to draw the stress cube for this point. Okay, well, the first thing we need to do is, so we're going to use the equation that says the Voigt stress is equal to the stiffness matrix times the Voigt strain. And remember, the stiffness matrix is just the inverse of the compliance matrix, so we could write it like this. And you don't have to know how to calculate that by hand or anything. Your calculator will calculate that inverse. So let me take a second, and I don't have this entered into my calculator, so let me enter in the compliance and then compute the inverse. And so the stiffness matrix is 1.03 times 10 to the 11th, 3.76 times 10 to the 10th, 3.76 times 10 to the 10th, and then 0, 0, 0. Then we have 3.76 times 10 to the 10th, 1.03 times 10 to the 11th, 3.76 times 10 to the 10th, 0, 0, 0. Then we have 3.76 times 10 to the 10th, 3.76 times 10 to the 10th, 1.03 times 10 to the 11th, 0, 0, 0. And then we have 0, 0, 0, 3.29 times 10 to the 10th, 0, 0. And then move that value along. And there's your stiffness matrix. And this has units of pascals.
Wait, not just the inverse of C, or did you multiply it by something to get that?
To get the units?
No, to get the
I didn't multiply. No, that's just the inverse. So I put C in there first, and then I took the inverse.
Okay.
And so now we're going to say the Voigt stress is equal to this E times the Voigt strain of 1.5 times 10 to the minus fifth, 0, negative 2.5 times 10 to the minus fifth, and then minus 6.0 times 10 to the minus fifth, and then 0, 0. Okay, and
Was what we get that? Is that the voice strength?
that is the Voigt stress
Right.
that we just calculated. And so now what I asked for was the stress cube. So we'll go to the stress tensor from here. So 6.11 times 10 to the 5, negative 3.76 times 10 to the 5, negative 2.02 times 10 to the 6, and then 0, 0, negative 2.02 times 10 to the 6. And now just make it symmetrical. So there's the stress tensor.
Where did the negative 1
I wrote down the wrong thing here. That should be this.
Same thing. Negative 2 to the power 6.
Yeah, it's pretty close, but I just wrote down the wrong number. Okay, so what this says is there's tension here of 6.11 times 10 to the 5th. There's compression here of 3.76 times 10 to the 5th. And there's compression here of 2.02 times 10 to the 6th. On the x face, there's nothing in the y direction, nothing in the z direction. On the y face, there is something in the negative z direction. So that's 1.97 times 10 to the 6th. And that means that there has to be something here of 1.97 times 10 to the 6th. I want to point out one thing here. Our strain, notice that the strain at this point there was no normal strain in the y direction, no stretching or compression, contracting in the y direction. So what's going on that there is internal loading in the y direction? Where does that come from? Well, that's that Poisson's effect. Okay, there's that dependency. Each normal strain depends on all three of the normal stresses, and vice versa. Each normal stress depends on all three of the normal strains. And so that's where, for the normals, you can have 0 for one thing and non-zero for something else. Okay, that doesn't happen with the shears. The shears only have the dependency on the corresponding shear element. But just think of how surprisingly powerful that is, that we could do such a simple, look how simple this test is. We just stretch this thing, measures the deformation along two directions, calculated these two parameters, Young's modulus and Poisson's ratio. And with nothing but that, we were able to predict, if we're given a loading at a point, what the deformation is going to be. And on the other hand, if we know what the deformation is going to be, we're able to predict calculate what the loading will be. That's a lot of computational power with a very little amount of experimental work. Okay, let's take the rest of the time and try to get this stuff entered into calculators. It took me forever to enter that compliance matrix because I don't have that program in here. But let's just go through the calculators you have one by one and just try to get these entered. So
I entered mine and it was just the matrix, there was a bunch of zeros and I helped plug.
Yeah.
36 just about like 18.
What do you have, an Inspire?
84.
84. Fancy looking. It's an inspired 80,
I got it up.
84.
Pieces.
Okay, so for an 84, I think for an 83, maybe you do something similar, but okay, so if you have a TI 84, go to Program, and
Do you want the 80?
oh yeah, that'd be great. Thank you. Okay, go to Program, and we'll call this CMPL for compliance. So go to Create New. And for the name, I'm going to enter CMPL. Now you don't have to do this. It'll be on yours. Win-win. Okay, so CMPL. And for the first line, go back to the Program button and go to Input Output and Prompt. And then enter the letter E. So it'll write prompt for you and you just enter E and then enter. Oh, that sucks.
Yeah.
That's all right. You can watch this video later. And now we're going to do the same thing again.
Is that the letter E? Or is that like
That's the letter E, yeah. Input, output, prompt, and I guess I'll just call this one V. So the letter V. And now, okay, this is where this is a pain. But what we are going to do is we are going to go to, so one of these things in the matrix environment. So go into the, while you're still in that programming editor, go to matrix. Actually, oh boy. Why don't you get out of the matrix environment, the programming environment for a second? Go into matrix and create a 6x6 matrix wherever you want. I guess I'll put it in matrix, edit, and
this matrix will have to stay like this then?
yeah, so you'll just use that as your, whichever one you put is going to be permanently your compliance matrix.
Okay.
And if you ever use it for something else, then later you just have to go back and reformat it as 6x6. So you're just making it in the right place. So 6x6. And now once that's there, okay, now we can go back into the programming environment. Okay, so now what we have to do, it's the weirdest thing on these calculators. Like it'll put text in as we do it, but if you enter in the text this way, it won't accept it. So what we have to do is, so now I'm in the programming environment, okay? And I'm going to go, while I'm in there, I'm going to go to matrix, and I'm going to scroll down to whatever matrix I have that I put the compliance matrix in. And then, so you're going to go matrix, you're going to select the one that you want. Mine is D. It's going to put this in place. So it's going to give you D. No, you don't want that. You want to say 1 over E. And then you want to use the store button to say this is going to go in. So this is where you have to do this thing. One. Okay.
How do you get the apostrophe? Oh,
And then we're going to do the same thing. We're going to go negative V over E, go back into the matrix environment.
Negative V over E.
Yeah, yeah. And you're going to fill all of these out So negative V over E is D 1, 3. Everything else is zeros already, so now we can go to the next line, negative V over E, and store that in D 2, 1. 1 over E, store that in D 2, 2. Negative V over E, store that in D 2, 3. Now we go to the third row, negative V over E, store that in 3, 1. Negative V over E, store that in 3, 2. 1 over E, store that in 3, 3. 3 values left. So then 2 times 1 plus nu over E, store that in D 4, 4. 2 times 1 plus V over E, store that in 5, 5. And 2 times 1 plus V over E, store that in 6, 6. Okay, and so now you'll have a program. I didn't do yours. I was too busy thinking. But now you have a program where when you call the program, it'll ask you what E is. It'll ask you what Poisson's ratio is. And when you enter that in, it'll put this matrix in what I have written as D, you know? And so now you can go get the matrix and use it for math. Okay. Okay. Some people have an 89. Is that right? You have an 84.
I have an 89 and 84.
So you're just going to use the 84?
Usually I use the 89.
Oh, okay.
That's a factor.
Okay. Do you have a minute after class and we'll just get yours entered?
Yeah.
Okay. And then the Inspire. Oh, the Inspire is great. Inspire is easy. So for this one, you're just going to go. Does anyone have an Inspire with them right now? Do you have it there? Can I look at it? Thanks. So for this one, you're just going to make this a function. Okay, I'm going to stop this and we're just going to figure out how to do it together. I don't remember.